So hello dear students. So can you hear me? Just write a message in the comment box. So let the other people also join us. So please mark your attendance. So today it is very important topic. So we are going to establish a connection between the microstate and we will derive the value of entropy, and from that we will derive the value of energy. So it is very important article of kinetic gas theory to find the thermodynamic parameters. So in our previous lecture we have derived the kinetic gas laws, and we have derived the relation of pressure and energy from those kinetic gas laws. And in our today's lecture we will study how to find the value of omega, that is how to find the microstates. So let us assume the classical system and we assume the particles, they are distinguishable. So the particle in state I, it get interchanged with a particle which is present in this system and having state J. So how they are exchanging their energy, how they are exchanging their other physical parameters. So from that it results in the microstate, it is counted. So we generally define the number of microstate as omega. So this is number of microstates. So this number, so if there are n number of particles which are present in a system, so having a energy that is of the order of E star, so in the state of equilibrium, so this defines a positive integral solution of the equation, so that we have already derived for the particle which is in a box, so that is for the three-dimensional motion. So this equation we have already derived, so that is of the order of E star. So it can also be stated that the number of microstates, it is equal to number of positive integral lattice point which are lying on the surface of 3n dimensional sphere whose radius, that is of the order of this under root of E star. So ਜਿਸ ਤਰ੍ਹਾਂ ਆਪਾਂ ਗੱਲ ਕੀਤੀ ਸੀ ਕਿ ਜਿਹੜਾ ਫੇਜ਼ ਸਪੇਸ ਦੇ ਵਿੱਚ ਜਿਹੜੇ ਆ, so if this side this is P, this side it is Q, and so there are small lattice representative points. So the value of this E star, it is something like having the 3n dimensional lattice point, so that is having of the energy of order E star. So for one particle, so if one particle it is present in this 3n dimensional sphere, so its microstate we can write it is something like omega 1 E in V. So this is the number of positive integral lattice points. So this we can generally represent in three-dimensional picture. So this is along x-axis, this is along y-axis, and the trajectory of this particle which will move along all these axes. So this defines the radius of this spherical trajectory, that is under root of E star. So similarly for n particles, so we can say the value is omega n. So these represents the number of positive integral lattice points on the surface of 3n dimensional sphere of radius under root E star. Now this number of microstate will be an extremely irregular function, because the number it can be very large, and the number of microstates for this n number of particles which are present in this three-dimensional sphere, so the microstate function it will be a irregular function of E star. So here E, that is representing the change in energy. So for only two given values of E star which are present in that spherical sphere, so the value of this change in energy it is very close to one another, and the value of this omega it could be very different. So to remove such irregularity, what we consider is we consider the another function, so that is this sigma n, which is also a function of energy, so which is defined as the number of positive integral lattice point lying on or within the surface of 3n dimensional sphere of radius under root of E star. Now what is the difference between this new microstate and this microstate? So this microstate says that the positive and integral lattice points, so they are present only on the surface of this sphere, while this says that because no system it is so much insulating, because the value of energy in a system it is changing time to time. So this says the number of positive lattice integral points, so they are lying on the surface or within the surface. So it is something like, so he has considered, so these lattice points they not only lie on the surface, they can also be present within this sphere, so they can be somewhere anywhere, so within this trajectory. So this represents the radius of this three-dimensional sphere. So this makes this new microstate a more precise or more regular function. So how we can find or how we can use this new microstate to solve the parameters. So this new microstate, so which is a function of nv and e, and the value of this e, it can be less than or equal to e star. So we generally represents so the microstate something like this. Now we have talking about the three-dimensional sphere. So this for one number of particles which are present on or on the surface of this three-dimensional sphere, so the asymptotic solution will be something like this. So that will be equal to the volume of an octant of a sphere. So this represents 1/8 part of a sphere. So because this trajectory, it is no longer a spherical trajectory, so it is something like a elliptical trajectory, and the volume for this microstate, it is the octant of a sphere. So octant means 1/8 of the sphere. So asymptotically the new microstate, it should be equal to the volume of octant of a sphere. So volume of a sphere, that we generally represent with 4 pi 3 pi r cube. So r is our under root of e star cube. So this we can write as pi by 6 e star 3 by 2. But you have to consider so this value. So let us say this is equation number 1. So similarly, for n number of particles, so if they are present in this sphere, so we can represent this new microstate, that is the volume of positive component of 3n dimensional sphere. ਹੁਣ ਇਸ ਕੇਸ ਦੇ ਵਿੱਚ ਕੀ ਹੈ ਕਿ if there are n number of particles, so then they can move in 3n dimensional degrees of freedom. So the volume of n particle, it is the volume of positive component of 3n dimensional sphere of radius under root of e star. Now the value of this volume, so we generally represent as pi n by 2, so that is for the spherical coordinate, n by 2 factorial multiply by the radius of this sphere. So this is for the n dimensional sphere, and for 3n dimensional sphere, this value we can write, so 1 by 8 we can write something like 1 by 2 the power 3n multiply by, so pi 3n by 2 over 3n by 2 factorial multiply by radius, that is e star 3n by 2. So this is the equation for 3n dimensional sphere of particles which are present in radius under root of e star. So this equation we can solve now. So this equation comes out to be, so let us change pen color. So that we have written 1 by 2 the power 3n into pi 3n by 2 over 3n by 2 factorial into radius, that is under root of e star 3n. So if we open this under root and this equation becomes e star 3n by 2. So this we can write 1 by, so what we have to do is we have to change all the powers of the order of 3n by 2. So how we can change all these powers from 3n to 3n by 2? So if I write it as 1 over 4 3n by 2 multiply by pi 3n by 2 e star 3n by 2 over 3n by 2 factorial. So this equation now we can combine and we can write it in the form of pi by 4 e star the power 3n by 2 over 3n by 2 factorial. So let us say this is equation number 2. Now from this microstate what we have to do is we know the value of entropy, that is equal to k log of this omega. Now our new microstate, it is from omega to sigma. So we have to take the logarithmic value of this equation 2 and from that we can find the value of entropy. So let us take log of equation 2 and this equation we can write log of summation nv e star, so that is 3n by 2. So the powers come in the beginning, so log of pi by 4 e star minus log of 3n by 2 factorial. So let us solve these two equations separately. So let us say this is our first term and this is our second term. So let us say this is equation number 3. So let us solve this first term and second term separately. So this equation, the first term, so first term is log of pi by 4 e star 3n by 2. So this we can write, so we have to put the value of e star. So the value of e that we know, that is 8 mv 2 by 3 e over h square. So this we have derived yesterday from the kinetic gas laws. So we have to put the value of this e star in this equation and this equation becomes, so log of pi by 4 into 8 v 2 by 3 e over h square the power 3n by 2. So when we get cancelled, so 4 get cancelled, so this we can write log of v 2 by 3 over h square, so that we write separately 3n by 2. So other terms, that is 2 pi me, so this is pi, so 2 pi me the power 3n by 2. So this equation becomes log of v raised to power n. So this 2 get cancelled with this, 3 get cancelled with this. So over h to the power 3n multiply by 2 pi me to the power 3n by 2. So take all the powers outside. So this equation becomes n log of v over h to the power cube 2 pi me to the power 3 by 2. So this is the equation that we have solved for the first term. So let us solve for the second term solution. So second term is log of gamma function of 3n by 2, or you can say log of 3 by 2 factorial. So using this Stirling's formula, this you have already discussed during your graduation. So Stirling formula says log of n factorial, that is equal to n log of n minus n. So similarly, so this log of 3n by 2 factorial, this becomes 3n by 2 log of 3n by 2 minus 3n by 2. So this we can write as n log of 3n by 2 the power 3 by 2 minus 3n by 2. So this is our second term. Now put the values of this first term and second terms. So the logarithmic value of our new microstate sigma, so this becomes n log of v over h cube into 2 pi me the power 3 by 2. So this is the first term which we have derived. So this one. The second term that we have derived, that is minus n log of 3n by 2 the power 3 by 2 plus this minus and minus, this become plus, so that is plus 3n by 2. So let us combine all the logarithmic values. So this equation becomes n log of v over h cube 2 pi me the power 3 by 2. So the second minus term logarithmic value, it goes in the denominator, so that is over 3n by 2 the power 3 by 2 plus 3n by 2. So let us further resolve this equation. So log of summation nv and e, so this is n log of v over h cube 2 the power 3 by 2. So the denominator term also goes upward, that is 2 the power 3 by 2 into pi me the power 3 by 2 over 3n the power 3 by 2 plus 3n by 2. So this equation becomes n log of v over h cube 4 pi me the power 3 by 2. So if I also include this term that is in the denominator within this bracket, so 4 pi me over 3n so whole power 3 by 2 plus 3n by 2. So this is the equation which we have derived for the logarithmic value of number of microstates. Now for the derivation of the thermodynamic properties of this system, so we must first of all have to fix this precise value of E. So this is only for a energy that is varying from 0 to E. So for the particles which are present on or which are present within the surface of a octant of a sphere. But in general, so the value of this E, it is no longer a precise value, because there is some heat loss or some heat gain which always happens within this system. So in real world, almost every system has some contact with the surrounding. So energy cannot be sharply defined. So we cannot sharply define that the system has this precise E value of energy. So energy values cannot be sharply defined. So there is some sort of effective width, that is of the range over which this energy that is varying. So we have added a limit that the range of energy, so when this system it is in the contact, so it is from a range that is from E minus delta 2 to E plus delta 2, where the value of delta, that is how much energy it is being varying, so the value of this delta, it is very small as compared to the energy values. Now we have added this one more physical parameter in our system, so therefore the number of microstates, so the corresponding number of microstates values, they also change. So our new corresponding number of microstates, it is generally represented with the term that is gamma, which is now dependent upon the four parameters, that is N, V, E and delta. So delta is how much energy the system it is being changing with respect to the surrounding. So sigma, that is the new microstate, so this we can calculate if we differentiate our previous microstates with respect to energy. So the sigma number of microstates, so this I have denoted with sigma sign, and this I have denoted with gamma sign. So these notations, so they are named different in different books, so you can use as per your convenience. So I have used this term as sigma and this term as gamma. So please note down. So the sigma number of microstates, this we have already derived in our previous slide, and whose value is V over h cube whole power n 2 pi me the power 3n by 2 over 3n by 2 factorial. Now what we have to do is we have to derivative of this equation which we have already derived. Now if I take the derivative of this term with respect to E, so this equation becomes v over h cube the power n 1 over 3n by 2 gamma. So derivative of this term I will take now. So the bracketed term, so I will write separately with some different color. So it comes out to be 3n by 2 2 pi me 3n by 2 minus 1 into again the derivative of the bracketed term, that is 2 pi m. So this equation becomes, I will write here, v over h cube the power n 1 over 3n by 2 factorial 3n by 2, or you can write it 2 pi me the power 3n by 2 and 1 2 pi me inverse, it goes in the denominator, and what we left with is 1 over e. So I am writing the direct results. So this equation becomes curly sigma over curly e. So you can use the calculations. If there is some problem, you can ask me on WhatsApp. So this equation becomes 3n over 2e v over h cube the power n 2 pi me the power 3n by 2 over 3n by 2 factorial. So again this term, that is our microstate sigma. So this we can write 3n by 2e into sigma nv into e. So the new microstate, that is gamma, which is dependent upon 4 parameters. So this we can write delta into curly sigma over curly e. So this is 3n by 2 into sigma nve over e. So in short, we can write it as gamma is delta over e 3n by 2 into sigma. Now what we have to do is, from this precise number of microstates, we can calculate the value of entropy, that is k log of omega. So taking the logarithmic value of this equation, log of gamma, so this becomes log of delta over e plus log of 3n by 2 plus n log of v over h cube 4 pi me over 3n the power 3n by 2 plus 3n by 2. So this is the value of sigma function. Now if in a system the number of particles, its number is very large, so the term this first term, which is the bracketed term, so let us say, so this is the bracketed term. So for a system which is having n very large as compared to 1, so the value of this log n over n, so that is of the order of 0, so when n approaches infinity. So the second term or the bracketed term, it is negligibly small. So what does it means? So thus far all practical purposes, the actual width, so the value of this sigma, it is almost equal to value of this gamma. So for a system whose n that is very large, having very large number of particles, so the actual width of this allowed range of energy, it does not make much difference. So for all practical purposes and for a very large system, so the actual width of energy range does not make much difference. So what does it mean? It means that the energy could lie between E minus delta 2 to E plus delta 2, or the results will be same for a system which is having a energy range from 0 to E. So the physical reason for this situation is that the rate at which the number of microstates of this system increases with energy is so fantastic that even if we allow all these values of energy from 0 to E, it is only the immediate neighborhood of E that makes a dominant contribution to this system. So we have derived these new microstates. So this is only valid so for a very small systems, and for very large system, so the sigma and the gamma microstates, so their results are almost same. So the stage is now set for driving the thermodynamic parameters of our system. So first of all, we will drive the entropy, so that is equal to k log of sigma, or you can say k log of gamma, because we are having general a very large number of particles which are present in our system. So S, it comes out to be nk log of V over h cube 4 pi me over 3n the power 3 by 2 plus 3nk by 2. So how we can find the relation of this entropy, so in terms of energy? So let us try to solve this relation. So if we divide this relation, so divide above equation with 3nk by 2, so this becomes S over 3nk over 2, that is equal to nk over 3nk by 2 log of V over h cube 4 pi me over 3n the power 3 by 2 plus 1. So this plus 1, if we move to the left hand side, so this becomes 2s over 3nk minus 1, that is of the order of 2 by 3 log of V over h cube 4 pi me over 3n the power 3 by 2. So if we keep this 2 by 3 to the power, so this equation is log of V over h cube 4 pi me over 3n the power 3 by 2 and the power whole power 2 by 3. So this equation becomes 2s over 3nk minus 1, that is log of, so if I take the logarithmic value to this side, so I can write this as the exponential function. So this is the bracketed term. So this left hand side, this becomes the exponential function of 2s 3nk minus 1, that is equal to V 2 by 3 over h square. So powers get cancelled and what we left with is 4 pi me over 3n. So from this, the energy, it comes out to be h square over V 2 by 3 3n over 4 pi m exponential of 2s over 3nk minus 1. So this is the expression of energy in terms of entropy value. So once we find out the expression of energy, from that we can find out the other thermodynamic parameters. So this is energy expression in terms of entropy. So that is for a 3n dimensional sphere for a energy range 0 to E. So from this expression, that is very important, so we can find out all the other thermodynamic parameters. So let us find the temperature from this equation. So temperature, which we have explained in our previous lecture, that is curly E over curly S at constant N and V. So taking the derivative of this energy expression with respect to entropy, so this equation, it becomes T, that is curly by curly S of the energy expression, that is 3n h square over 4 pi m V2 by 3 exponential of 2s over 3nk minus 1. So what are the terms in which the S is present? So all the other terms, so these are independent of S, and we take these constant terms outside. So 3n h square over 4 pi m v raised to power 2 by 3, it comes outside, and we will take the derivative of only the exponential function that is exponential of 2s over 3nk minus 1. So this we can write as 3n h square over 4 pi m v2 by 3. So derivative of exponential function as it is comes outside 2s over 3nk minus 1, and the derivative of the bracketed term, so that is 2 over 3nk. So this is the derivative of the bracketed term. Now if you look at this value, so this is again the expression of energy. So value of T, it comes out to be 2E over 3nk. So from this we can check whether the energy expression which we have derived for a particular system, so the value of this 3, it is coming of the order of 3 by 2 nkt. So that is following the kinetic gas laws. So from this we can check that the expression of this energy which we have derived, so that is all correct. So this is how you can counter check your expression. So similarly we can find the pressure term. So pressure, that is of a system, that is minus curly E over curly V at constant n and s. So again you have to take the derivative of the expression of energy. So this we can write minus curly over curly V, so exponential of 2s over 3nk minus 1 into 3n h square over 4 pi m v2 by 3. So again, so only the terms so which have the function of volume, that will be remain within the derivative function. So all the other terms, so that will come outside. So the exponential function that is independent of volume, so it will come outside, and we will take the derivative of 3n h square 4 pi m. So the derivative of the volume term, that is minus 2 by 3. So this equation becomes minus exponential of 2s over 3nk minus 1 over 3n h square over 4 pi m into minus 2 by 3 volume of minus 5 by 3. So this we can write as 1 over v raised to power 5 by 3, or you can write this equation as this minus and minus, they get cancelled. So 2 by 3 into 1 over v 3n h square over 4 pi m v2 by 3. So we have break down this v 5 by 3 in terms of v into v2 by 3. So this exponential of 2s over 3nk minus 1. Again, so this is the expression for energy. So the pressure terms, it comes out to be P by 3 into E over V. So from this you can say the value of P, it is following the kinetic gas laws. So similarly, what I want to say here, so once you find out the microstate of a system From that you can find out the value of this entropy, and from this entropy values you can find the all the other thermodynamic parameters. So what we have derived the value of energy from this entropy, and from this energy we have derived the value of temperature. From this energy we have derived the value of pressure. So similarly you can derive the value of specific heat of the system, that is curly E by curly T. So it comes out to be 3 by 2 nkt. So that the of the order of 3 by 2 nk, or you can write it in terms of 3 by 2 n into r, because n is n into Avogadro number. So similarly you can calculate the specific heat at constant pressure, that is E plus PV. So this equation is curly by curly T 3 by 2 nRT plus PV is again nRT. So it comes out to be curly by curly T of 5 by 2 nRT, and from that you can calculate it is coming of the order of 5 by 2 nR. So this is the value of Cp and this is the value of Cv, and from that you can find out the ratio of these two specific heat that we generally represent with gamma. So Cp over Cv, that is 5 by 2 nR over 3 by 2 nR, so that is equal to 5 by 3. So from that you can check whether the gas which we are following in our system, that is a monatomic gas or a diatomic gas or a polyatomic gas. So here I want to mention some important points. So if the gas undergo isothermal change of state, so in that case the value of T for a isothermal system, so that is constant, as the value of N is constant, while the pressure term it is having a value nRT over V, so which would vary inversely with volume. So that is our Boyle's law. So similarly, if the gas which is in our system, it is having a reversible adiabatic change of state, so in that state, so for a adiabatic system, so the value of this entropy, so that is constant. So in that case the E and T varies inversely proportional to V 2 by 3. So we can find out the adiabatic parameters, or we can derive the relation of P V the power gamma, that is coming out to be constant for a adiabatic system, or you can check the value of TV gamma minus 1, that is coming out to be constant. So this you can check or explain whether the system which we are following, whether it is a classical system or it is a isothermal or it is a adiabatic system. So this is very important article, how to find the thermodynamic parameters for a classical ideal gas from the microstates. So this is the connection between the microstate and a macrostate, and they can ask you to explain the importance of this microstate and how its value that is varying for a precise energy limit or for a energy range that is from E minus delta 2 to E plus delta 2. So in our next discussion, so the entropy term which we have derived, so in this lecture, So that is not the exact correct term. It is not always the correct term for a reversible as well as a irreversible system, and it demands some further modification. So this has been explained by Gibbs, and he resolved this entropy term and he derived a new entropy term, and that resolution is known as the Gibbs paradox. And that entropy, we will check how the value of this entropy it changes by implementing the results in various systems. So I hope you have understand this lecture. So if you have any doubt, you can write your comments in the comment box. So let me check how many students again they are present. So students, please write down again your roll number in the comment box to mark your attendance again. So I am checking how many students, so they are marking their presence again. So I will share these notes with you, and I will also provide the notes of my handwritten notes which I have made by following 2 or 3 books. Yes, okay. So others also mark their attendance. So then we will close our discussion for today. So one point I would also like to say is, please try to write these expressions with your own practice, do your own practice, because otherwise in the exam you will stuck in these differentiation or derivative calculations. So this is very much important. You do this expressions and try to drive these expression uh, with your own practice. So for the reference books, some of the books students they are asking about the reference books. So there are 3 reference books which we will follow. One is of statistical mechanics by Pathria, and second is statistical mechanics by Satya Prakash, and another very important book is the statistical and thermodynamics by F. Reeve. So I will write here all the authors. So one is Patharia, so very old and famous book. So approximately 60 to 70% of your syllabus it is covered in this books. So Satya Prakash, it is also again a very good book, and the concept it has been explained in easy way and in detail. So this is a very good book. Another book for more concept clarity, you can follow this F. Reef book, that is also a important reference book. So these 3 books you which will cover all of your syllabus. So you can choose any book. So okay dear students, till then goodbye. See you in the next lecture. Hello. Hello.